All right, so this week, all we're going to do is finish up Chapter 5, which has to do with log functions. Okay, so we'll look at solving a few equations. We'll also do a little bit of graphing, and we'll talk about transformations with logs. And they work exactly the same way. We've talked about transformations for everything else. All right, so just kind of as a review question, I just want to start by rewriting this using properties of exponents. All right, so whenever you have addition in an exponent, what does that mean must have happened originally? When would you be adding things together to calculate an exponent? Yeah? Yeah, if you're multiplying things with the same base, you would have been adding exponents. And what about when you subtract exponents? Yeah, when you're dividing. All right. So forget about the minus z part for now, but anybody tell me how I could rewrite a to the 2x plus 3y? What would that have been originally? Think about if I had something like this. Yeah, you'd have a to the 2x times a to the 3y. Okay, and this one I was going to say would be like 2 cubed times 2 squared. Right? So it would have been a to the 2x times a to the 3y. And now what about the minus z?
Over a to the z.
Yeah, over a to the z. So all they want us to really do is rewrite this so you have an a to the x, an a to the y, and an a to the z. Okay, we've got an a to the z. But I don't have an a to the x yet. I have an a to the 2x. So here I'm multiplying the 2 and the x. When does that happen? When do you multiply numbers to calculate your exponent? Right, so can you tell me how you would rewrite this? So it was... Yeah, you could write either way. You could write a squared to the x or a to the x squared. I'm going to write it that way because that's what they wanted me to get in the final answer. So I have an a to the x times, and now I'm going to do the same thing for a to the 3y. It's a to the y cubed. So I've got an a to the x, I've got an a to the y, and the denominator already had an a to the z. All right, so that was really just practicing a little review of our rules for exponents. Okay, any questions on that? All right. So let's take a look at a problem we've already done. Okay, it has to do with like a population of a town either growing at a certain percent or going down at a certain percent. But when we solved it before, we did it graphically. All right, now that we know a little bit about logarithms, we can solve it algebraically. So you already have this problem in your notes, probably from probably the last section. Okay, so some people double checking. Did anybody find it? Town with a population of 50,000 people, increasing at 2.5% per year. You found it? Okay. Is all the numbers the same? 50,000, 2.5%?
I wrote down a 50,000 increasing rate of 2.5%.
2.5%. Okay, so yeah, we've done this problem before. But if you want to copy it again, you can. And I want to know when the population is going to reach 100,000 people.
So we did it on November 8th.
Yeah, probably when we did 5.4 part 1.
It was 5.1.
Thanks, David.
Oh, 5.1? Okay.
I was wondering.
I write the dates down.
So what's our formula for exponential growth? Anybody remember how we write that? Or what do we start with? Yeah, Dave?
P,
Which is what?
population.
Yeah, the population, the initial amount. So 50,000.
of the C.
1 plus R.
Yep, 1 plus R. And what's my rate here?
0.02.
0.025, because we have to write it as a percent. So 1.025. And then that's raised to the t. Right? And it's increasing 2.5% every 1 year. Okay? So yeah, it would just be t. It would be a divide by 1. Okay, but we don't need to write it. If it said the population increases at 2.5% every 3 months, then we'd have to put a divide by 3. Okay, but it just says every 1 year. All right, and we want to know when the population is 100,000. So where does the 100,000 get plugged in?
At the AT.
A of t. That's the amount of people as a function of time. Or you could write P of t, population, as a function of time. Okay, however you want to write it. Okay, so we have 100,000 equals 50,000 times 1.025 to the t. Now, just by looking at that equation, what in that equation tells you you're going to have to use a logarithm at some point to solve it?
The exponent.
The exponent. What kind of exponent do I have? It's a variable. Anytime you have a variable as an exponent, that's kind of your hint. You got to use a logarithm. Maybe not right away, but eventually. So my goal is to get t by itself. Does anybody see anything I could move to the other side first? Yeah? Yeah, I could divide each side by 50,000. And divide by 50,000. Okay, and Ellie, if I divide by 50,000, what's 100,000 divided by 50,000? Yeah, 2. All right. And now what would I do? What's the only thing I know how to do with something like that? Remember what we can do with that? Something we learned, I think, back in section 5.4. Let me bring it up. All right, so one way we could do that is to change it to log form, okay, as we just discussed. But the problem is the base there is 1.025. Okay, so changing it to log form, you would get this. Log base 1.025 of 2 equals t. Now, if you know how to type that in, you're all set. Okay, and the bonus question on last week's test was something like that, okay, to figure out a base other than base 10. So if you already know how to do it, perfect. You just type that in. If not, I'm going to show you a different way to solve it. Okay, I'm going to go back to this equation, and I'm going to take the log of each side. Log 2 equals log 1.025 to the t. So I just took the log of both sides. And now what can I do with that t? There's a rule we have for, yeah, you can move it in front. So now I have log 2 equals t times log 1.025. And now how could I get the log 1.025 on the other side? I could divide. And that, what I'm about to do, might give you a hint at the formula I'm going to show you in the next section. That's what you need to type in. Log 2 divided by log 1.025. So it ends up basically being the log of the argument divided by the log of the base. That's the shortcut, so we're not going to have to go through this every time. Okay, we'll be able to jump right to what I circled. Okay, now there's no base on the log here. So when I took the log of each side, what base did I use? 10. I used 10. Okay, so just type in log 2, make sure you close your parenthesis, divided by log 1.025. Okay, and we get 28.07 years, okay, because our problem was measured in years. So we get 28.07. Bless you. Any questions on that? All right, so if you wanted to do it graphically, the way we did it in the section 5.1 is we put 100,000 in y1. We put 50,000 times 1.025 to the t in y2, and we see where they cross. Now we have a way to do it algebraically, okay, using a logarithm. Okay? And again, you're going to have an even faster way to do it without taking the log of both sides and just jumping right to this final step. Okay. So, any questions on solving a log equation, either algebraically or graphically, which I didn't review, but we did it before? All right, so the last thing we're going to look at in 5.4 part 2, okay, is more of a statistics thing. All right, so sometimes in Algebra 1, you might have some points that when you make a scatter plot, they kind of look like they're close to forming a line. Okay? And you can draw or calculate what's called a line of fit. And if you take statistics, you'll probably learn the method for calculating what's called a line of best fit, which gives you the best possible slope and best y-intercept to fit some data. Now, does this data look like it's linear? No, it's definitely not linear. So if I try to put a line through it, I can. You know, it just might be something kind of like that. But the data isn't really linear. It's more of a curve, okay, like that. So what we're going to learn how to do is calculate a curve of best fit, okay, for that kind of data. And specifically, we're going to look at an exponential curve. Okay, and that's the kind of equation that we're going to use. Okay, we'll do one just calculating it out by hand, and then I'll show you how to do one on the calculator as well. Okay, and that's known as a power function. Okay, when we get to doing it on the calculator, I'll have to be careful with which equation we use. We'll have to double check because the calculator might call it something different than our book. Okay, but I'll double check that when we do it. Okay, but that's the word your book uses, power function, and that's on page 290. Okay, so the goal when you have a power function is you need to calculate A and M. Okay, those are the two things that you need to find. So when you're done, your answer might look something like y equals 1/2 x cubed. Okay, something like that. You're going to leave the y and the x, but you have to solve for the A and the M. Okay, and they'll give you a set of data to do that. Right, but before you can use a power model, you have to know if that's what you really should be using. Okay, because if you just have a set of data, okay, like let's look at this. How do I know whether or not I should use a power model for that data? I mean, I could draw it and see if it kind of looks curved, but there's got to be some way we can do a calculation and see, is this the right kind of data to use a power model for? Okay, or should we do something else? Right? So I'm going to show you how you figure out if the power model is the right tool to use. And then I'll show you how to do it, if it is.
Did you just find the slope between all of them? They have the same slope?
It's kind of what we're going to do. Yeah, we're going to basically see something to do with slope. Right? So what I'm going to do is I'm going to take this equation. I'm going to show you a series of steps with log rules. And it's going to kind of lead us to the idea of having a slope and a y-intercept. Okay, so what I did here is I took the equation we had, and I took the log of both sides, okay, specifically the natural log. Now, once I take the log of both sides, I get ln y equals ln of ax to the m. How does a logarithm with a product split up? If the argument is a product. It splits as addition. Right? So I could write it as natural log y equals natural log a plus natural log x to the m. And now something I think we either did it probably earlier today. That exponent of m, what can I do with it? I can put it in front. Now, that equation, that last one I have, it isn't exactly like that. But basically, if you took y equals mx plus b, and you put an ln in front of everything, ln y equals m ln x plus ln a, and that's a different letter, you'd pretty much have the same equation. So what that means is natural log y is the linear function of natural log x with a slope of m and a y-intercept at ln a. It's a little, weird to kind of think about it, but that's what that means. It means not y is a linear function of x. That's this. Okay. What we're saying is natural log y is a linear function of natural log x. Okay. And the slope would be m, and the y-intercept would be ln a. So what this is getting it at is basically you can use a power model for the data as long as ln y is a linear function of ln x. Okay. That's how you can tell whether or not you should use a power model. Okay, so to determine if you should be using a power model for your data, okay, to try to find a curve that goes through the points, the best that it can, you're going to be given a table. And the first thing you're going to do in that table is you're going to take the ln of everything in that table. All right, so they're going to give me a table of data. I'm going to take and find the ln of all 8 of those numbers. And I'm going to make a new table. And that table is purely just to test if I should be using a power function. Okay? Once I know whether or not I should use a power function, I can throw that table away. I don't need it. The only thing I need it for is to find out if I should be using a power model. So take all your data points, find the natural log of all of them, which we can do pretty quick on the calculator. And then once we know a power model is the correct thing to use, okay, we'll find A. Okay, we'll find that first. Okay, and we're going to use that equation to do it. And once we have A, then we find M. And again, we can use that equation to do it. And then we just write our final answer. Okay, filling in for A and for M. Okay, and remember, once you fill in, you want your final answer to look like this. We're going to use that equation I put a box around to get the A and the M, but when we're done, we're going to put our answer in that form. All right, so let's just go through an example and see how we do a power model. Okay, we'll do it twice. We'll do it once by hand, and then we'll do it once with the graphing calculator. All right, so this time they're not telling me whether or not I should use a power model. First, they want me to figure out, basically, should I use a power model? And if I should, then do it. Okay, so the first thing I'm going to do is I'm going to make a new table, just temporary. I only need it for step 1, just to check if a power model is the right thing to use. Okay, so I'm going to take the ln of all 8 of those values. And remember, I'm trying to see if it is a linear function once I do that. Okay? I'm going to try to see that if I graph this new table, do these points line up in a straight line? If they're pretty close to a straight line, then a power model is what I want to use. Okay, but it's not the original table that should lie in a straight line. It's the ln table. All right, so let's go through and find all those values. Okay, so I've got ln1, ln3, ln5, and someone could do the bottom. That would help us out a little bit. So I'm going to copy those values down. So I've got 0. Let's just say about 1.1. Rounding to the nearest tenth is good enough because we're just going to make a quick sketch and see if these points are in a line. Right? So 1.1 is fine. 1.6. And about 2.1. Okay, does anybody have the, well actually I already know ln5 because I did that one. That's 1.6. 3.4?
Yeah, and then 4.3.
4.3, yep.
5.1.
And 5.1. Okay, so now I'm going to check and see if lny is a linear function of lnx, just by graphing those points. I can do this by hand, or faster way would be on the calculator. So 0, 1.1, 1.6, 2.1. Okay, and 1.6, 3.4, 4.3, 5.1. Oh, 4.3 and 5.1. All right, so I'm going to look, all these points are in the first quadrant, okay, pretty much, except one of them is going to be on the axis, 0, 1.6. So I don't need to look at any negative values really, but if you do a zoom 6, it should be okay. Only thing I have to do is make sure that I turn on my stat plot. If I don't turn that on, I won't see any points. So do those points look like they're in a straight line? Yeah, they're pretty close to a straight line. So that means, yes, a power model is probably the right tool. The straighter they are in a line, the better the power model is going to work. Now I'm done with that table. I don't need this table for anything else. Okay. So any questions on how I know a power model is the right tool? Yeah?
This is going to be a stupid question, but how did you get the chart up so you can enter?
Oh, you press stat and then edit,
Okay.
and then you can type your X's in L1 and your Y's in L2. Yeah. And in fact, I can clear these out now because I'm done with them. All right, so I'll come back to that in a second because we are going to use the calculator to do this, and we're going to end up typing the original table into the calculator in a little bit, okay, after we do it by hand the first time. All right, so first thing they want me to do is find A. My suggestion to find A is if you have a point with a 1 in it, use that, because when you take the ln of it, you get a 0. And zeros are very easy numbers to work with. So I want you to take this equation and fill in the x and the y value right there. Right, so I'm going to write ln5 equals m ln x. And remember, for x, you're going to fill in 1. Because this is going to work out very nice if you do it this way, plus ln a. All right, So I get ln of 5 equals, what's the ln of 1? 0. And what's 0 times m? 0. So basically that term cancels itself out. So ln 5 equals ln a. So by looking at that, what does a have to be? A is 5. Okay, so that's one thing I need. That's my base, okay, when I write my final answer, which I covered the equation up, I think. So that's my base. And now I'm going to find m. Okay, that's my exponent. Now to find m, you can pick any other point you want in that table and just plug it in again. Just don't pick the same point. Pick a different point. But now I know a is 5. So I know the a. I'm going to know the x. I'm going to know the y. I just need to solve for m. All right, so let's, doesn't really matter which one we pick. Let's do 8 160, just because it doesn't have any decimals in it. So let's plug that one in. So now take this and that and plug it into that equation I just put a box around. Okay, and solve for m. All right, so we've got ln of 160. Okay, it's almost like solving for slope in y equals mx plus b. You're plugging in a coordinate, you're plugging in the intercept, and you're finding the slope. It's basically what we're doing. The only difference is you've got ln's all over the place. Okay, that's the only difference. So ln y equals m times the ln. What was the x value that went with 160? 8. Thank you. Plus, oh, I don't have to go back up. Plus ln of a, which is ln of 5. Now, on the right-hand side, I'm seeing that I'm adding two ln's together. So that's one thing I need to think about. And I have an m in front of the ln. So let's start with that. When you have something in front, what are you allowed to do with that m? Put it where?
ln5. Right?
Well, the m doesn't have anything to do with the ln of 5. It has something to do with the ln of 8. Yeah, put the m back as an exponent. Okay, what I'm starting to do is recombine everything on the right-hand side into one log, not two. And now if I want, I can do something else in the same step. What, if you have that L plus ln of 5, how would that have been originally? It would have been multiplication. Just like that. Any questions on that step? So put the m back as an exponent, and I recombined two logs that were addition to what they originally were before you split them into multiplication. All right, now the next step might be a little tricky, but what do you notice is on both sides? Yeah, now we said earlier you're allowed to take the ln of both sides of an equation, but you can also cancel it out from both sides. So you can end up with just this. It doesn't really matter if I put 8 to the m times 5 or 5 times 8 to the m, same thing. And now this is actually just like the population problem. Solve for m. All right, so what can I do with the 5? Yep, divide by it. Okay, that's like dividing by our initial population. And 160 divided by 5, I think it's 32. Yep, so 32 equals 8 to the m. And now there's a couple ways you can solve this one. Notice that 32 and 8 are both powers of the same number. That gives me a trick I can do here that I couldn't do on the population problem, because I couldn't think of a number in my head that 50,000 and 100,000 were both powers of, and they're pretty big. So the way we did this one was probably the best. But did anybody see what 32 and 8 are both powers of? And if you don't, we can go back and do it the way we did the population one. But if we do, this will be faster.
2.
Yeah, they're both powers of 2. I can write 32 as 2 to the 5th. And I can write 8 as what?
2 thirds.
Right, it would be 2 to the 3rd to the m. So what would that be? 2 to the 3rd to the m. Two to the what? Yep. So now we've got 2 to the 5th equals 2 to the 3m. So the bases match. What else has to match?
5 equals 2.
Yeah, 5 has to equal the 3m. Divide by 3, divide by 3, and there's your m. So now we've got A, we've got m. Just write them, plug them in, and write the final answer. It's y equals ax to the m. Right, so what did we have for A? A was, yep, A was 5x to the m. That's your equation that would go through those points, the best we can find. Right, so now what I'll do is, let me graph that line, let me graph the points, and let's see if that actually goes through them. Okay? But at this point, we've finished the problem. Okay, now we'll check our answer. All right, can someone tell me, so I don't have to keep scrolling up, what are my x values in the original table? 1, yep. 3? All right. 5? 8. All right, and I know the last y value was 160, but I don't remember the rest. 5? 31.2. 73.1. And 160. Thank you. All right, now to see these, let's see. I'm going to set my x min and my y min. What was the biggest x value? 8?
Yeah.
All right, so 10 is good. And the biggest y value was 160, so I'm just going to go a little past it. Okay, so there's your points, okay, from the original table. Now I'm going to type in that equation. Y equals 5x raised to the 5/3. 5x to the 5/3, and let's see how good that line goes through them. And it's going to go through pretty good. Okay, so we found a curve that goes right through those points. Okay, any questions on how we did that? Okay. Kind of new, but it's the same idea as y equals mx plus b. You've got to find your slope and kind of your y-intercept. And I'll always give you one with a ln where I give you 1 and then something. So that way when you put it in your ln table, you'll always get a 0. And that makes it easier. If you didn't get a 0, that's a little harder. So we're not going to do it that way. Okay, if you used another point here, it might come out a little different depending on the accuracy of these numbers. Doesn't look like in this table they rounded very much. I mean, they didn't round very accurately. But on a test, what I would probably do is give you at least 2 or 3 decimal places. So no matter which one you pick, all the answers are pretty much going to come out the same. All right, so any questions on that? All right, so now let me show you how to do the same thing on the calculator. Okay, in this part, I'm not going to write down all the steps, so if you want to write anything, you can. Or you can watch the video and just look at the steps. But step 1, okay, is you have to type in all the data. Okay, I already have that. Okay, so that would be my first step. Press Stat, go to Calc. I'm sorry, go Stat, go to Edit, and hit Enter. So Stat, Edit, and then hit Enter. And you can try it if you want, on your calculator. Okay, I've got my table of data in there. And now the next thing, I just want you to watch for a second because I want to double check that I'm doing it correctly myself. Let's see if I get. All right. So that tells me which way I want to do it. Okay, so now once you have your data in, press stat again, go to calc, and on my calculator it's the, well, it's the option A. Okay, power regression. So after you have your data typed in, press stat, press calc, go to power regression. And you know what I can do? I can put just put the main screens in the video so you can check them out if you need to. So there's your data. Then you go into calc, power regression. It's not happy with me right now, so I can't put that for you. But that's your next step. Go to power regression. Okay, as long as you typed your L1 and L2 just like I did, put your X's in L1, put your Y's in L2. Don't use the other lists. You don't have to change anything. Okay, just go to calculate, hit enter. And it tells us the equation is A is 4.9999 and B is 1. Looks like almost 6 repeating. Okay. Is that what we got for answers? Yeah. We got A as 5, which is what it really should be. And we got B as 5/3, which is the fraction 1.6 repeating. All right. So if I ask you to do it by hand, you have a way you can check your answer pretty quick. Type in your data and then calculate a power model. Right, so any questions on doing a power model by hand? Or using the calculator, because that's also important. Okay, and if you always want to double check that your answer is right, just type it in, graph it, and see if it goes through the points. If it doesn't, then something's wrong. Okay, so on the day of the test, I won't show you how to do the power model. Like if you say, I don't remember what button or what menu to go into, I won't show you. So any questions on how I got to these menus? Yeah, you could just look at the video. It's right in there. Yep. All right, so the last thing we're going to look at is section 5.5. And it's a little bit on graphing log functions. Okay, so since we can't graph bases other than 10 or e, or we don't even have buttons on the calculator for things other than base 10 or e, we need a way to type in things that are not base 10 and base e. And there's 2 ways you can do it. I would just learn one of the 2 ways, okay, but they're the same thing. So if you want to type in something that doesn't have a base 10 or a base e, what you basically can do, if you want to use common log, take the common log of the argument, put that on the top, take the common log of the base, put that on the bottom. And that's it. So if I wanted to know, like, what is log base 6 of 4? I don't have a base 4 button, but what I can do is I could type in log 6 divided by log 4. And that's the answer. Now, if you don't want to do it with log, you can also do the same thing with ln. Take the natural log of the argument, divide by the natural log of the base, you will get exactly the same thing. So I would learn just one of the 2 ways. I usually use the common log, but that's up to you. So now, using that formula, we can now graph things other than base 10 or base e. So could someone tell me how I could type in, and I'm going to turn my stat plot off because we don't need that anymore. How could I type in log base 3 of x? And let's do it as a common log. Yeah?
Log of x.
Log of x, yeah.
Divided by log of 3.
Yeah, that's it. Log of x divided by log of 3. Very important you close your parenthesis, just like I did here. All right, and let's do zoom 6. And now they've asked us a couple questions like, what is the domain and range? Okay, so what's your domain there? Think about your domain for any log function. What kind of numbers are you allowed to plug in for x? Positives, yes. You can't include 0. Okay, you can try. Go to your table. Try to plug in 0, it doesn't work. Try negatives, it doesn't work. Okay, so the domain is from 0 to infinity. And how about the range? Any thoughts on the range? I would not trust that picture. That picture is not right. It's as good as the calculator is going to do, but it's not right. So the range is not -2 to infinity, if you were thinking that. It does. It just keeps going down forever and up forever. So what's the range? All real numbers. I can show you that it's really not -2 because if I zoom in, everyone agrees hopefully it looked like it's stopping at -2. If I zoom in now, it looks like it's at -3. So what's happening is because it's getting so steep, the calculator can't sketch it. You can verify that it goes even lower than -3 by plugging in a very small x value. Now I'm at -4. Okay, and the smaller my x value, the further down it really does keep going. Okay, so range is -infinity to infinity. Okay, so 2 points in that problem. 1, don't trust the screen because it's not always right. And 2, that's how you type something in with a different base. Okay, all the transformations that we learned apply to the logarithms as well. All right, so can somebody tell me, you don't have to tell me all of them, but what A would do to this? What kind of transformation is that? Yep, that's your horizontal shift. What about B? Yep. That's your horizontal stretch, and A and B do the opposite of what you would expect. Okay, we've talked about that. What about C? That's your vertical stretch, and what about D? That's your vertical shift. C and D do exactly what you would expect. Okay, so I'm not going to write it all out because it's the same, and we've done it so many times for tons of other functions. All right, so first I want to know, very simple transformation. I'm only doing one thing. It's basically like I'm making B -1. That's all I'm doing. So I want to know how log base 3 of -x would compare to log base 3 of x. What's that negative, if I make B -1? What is that going to do to the graph? Yep. Oh, go ahead, someone. What do you mean? Can you describe the transformation like geometrically? Like, is it a shift? Is it a stretch? It's a flip. It's a reflection. Over which axis? Because that's important. Y. Okay, that's going to flip. That's your horizontal. Okay, so what's going to happen is if you had a point here and you reflect horizontally, that reflects over the y-axis. Right, so how can that graph be obtained? Right, so to graph log base 3 -x, reflect log base 3 of x over y-axis. Now we already know the domain and range of log base 3, so I want you to think about what it would be if you reflect it over the x-axis. Think about how it looks, the original. What would the domain be if you reflect that over the
Would be from 0 to
y? I think I missed y-axis. Yeah, it would be from negative infinity to 0. And what about the range? It went up forever and down forever before. So reflecting it, really any reflection here wouldn't make a difference. Or shift or stretch. The range is always going to be negative infinity to infinity. And now, where is my vertical asymptote here? It gets closer and closer to what value, but never reaches it. Yeah, it can never reach 0. This graph just comes down and gets very, very close. Now, what if you reflect that graph? What's the vertical asymptote then? It'd still be 0 because the vertical asymptote is the line of reflection. Right? That it's on the y-axis. So anytime you mirror image something, if you had any points that are on the line you're mirroring, it's right on that line of reflection, they don't move. Okay? So the vertical asymptote doesn't move. X equals 0 or y equals 0? X. Okay. And I think that's all they wanted for that one. All right, how about, yeah, we can take a look at this one. Log 3 minus x. I'm going to give you a hint. Okay, how many transformations are happening here? 2. What are the 2? Okay, horizontal shift, and we already talked about that negative. Which one do you do first? Yep, and that's going to shift which way? 3 to the left. Yep. So shift 3 units left, and the negative, that's a reflection over which axis? The y-axis. That's that one. Okay, so next I'll show you how you graph a log function. Okay, basically, when you graph a log function, there's a vertical asymptote. You want to find where that goes. And then if you can find the x-intercept and y-intercept, that can be helpful. But remember, not every log function has to have a y-intercept. We just did one that didn't. Okay? And it's also possible it doesn't have an x-intercept either. Okay? Think of a log function that looks like this. Okay, but we can try to find them if they exist. If not, I'll just use my table on the calculator to get some other points, and I'll just go with those points. Okay, so to find your vertical asymptote, what you want to do is take the argument to the log function, set it equal to 0, and solve it. That'll tell you your new vertical asymptote. And then to find your intercepts, that's just like it always is. To find the x-intercept, plug in 0 for y. To find the y-intercept, plug in 0 for x. And don't worry if you get something that doesn't seem right, because it is possible you don't have an intercept. And in general, you're always going to need some more points than just the intercepts. Okay, it's helpful to find, 3 or 4 points maybe, and that'll give you a good idea of your curve. Just remember, you can't take the log of a negative. If you try to on the calculator in your table, it's going to say error. Okay, it just won't give you a point. Okay, so we've done that before. That's just using the table on the calculator. All right, so let's try to sketch a graph of log base 2 of 3x plus 5. And we're pretty much going to answer most of these questions just by drawing the picture. You kind of have to figure out the x value, and you have to figure out the asymptotes. So answering those questions is really part of the sketch. Okay, first thing I want to do is figure out where my vertical asymptote is. Okay, how do I figure that out? We say, what was that first thing you want to figure out your asymptote? You take something and set it equal to 0. What do you set equal to 0? Yeah? The argument, which is 3x plus 5. Okay, so take 3x plus 5, and whatever value makes the argument equal to 0, that's your vertical asymptote. So we get x equals negative 5/3. So that's the vertical asymptote. And now the domain is either numbers bigger than that or smaller than that. Would I have to plug in numbers bigger than negative 5/3 or smaller? And remember, you always want this to be positive. If you're not sure, pick a number that's, let's start with bigger. Pick out what's a number that's bigger than negative 5/3. 1, sure. If I plug in 1, what do I get for an argument? 8. Can I take the log of 8? Yeah, 8's a positive number, so it worked. So since that point worked, all points that are bigger than negative 5/3 work. Right? So the domain is everything from negative 5/3 bigger. If you want to double check, try a number smaller. Try negative 10. That's a lot smaller. 3 times negative 10 is negative 30, plus 5 is negative 25. You can't take the log of negative 25. Okay, so we've got to pick numbers bigger than negative 5/3. Okay, so now I'll make my sketch. Okay, put a line. What is negative 5/3 roughly as a decimal? Yeah, about negative 1.6. Okay, so the best we can, just put a line right about there. And now from here, I'm going to use my calculator to get some other values. And I am going to have an intercept here. So I'll let x equal 0, and I'll find what it is. All right, so we're typing log of 3x plus 5. Okay, divided by log 2. Okay, that's my change of base formula. Let's check negative 5/3 just to make sure that's that's an undefined value. It should be. Okay, so anything bigger than that should work fine. Okay, so there's my intercept. Okay, and I'll use those values. You don't have to use just those values. Okay, just pick a few that are spaced out. Okay, so 0, 2.3. 2, we're at about 3.4. 5, 4.3. I can kind of see it's leveling off a little bit. And 10, we're at 5.1. Now, it's going to head to the right forever. It's going to not go past negative 5/3. How low does the graph go? Yeah, all log functions go either up or down forever. It just depends if you flip it. Okay, so it's going to come in, curve down, and that's what it looks like. Okay, so very similar to graphing other functions. Kind of find that start point, or in this case, our asymptote, which tells you where the graph doesn't go past, and then it goes in one direction from there. Okay, any questions on that graph? All right, so the last problem, we're not going to go through deriving the formula. I'm just going to tell you the formula. Basically, all you have to do is plug into the formula and calculate the answer. So it's the formula for the Richter scale. So when they say like you have a magnitude, 2.5 earthquake, that's the formula they use to figure it out. So R, that's the magnitude. That's the number you usually hear about the earthquake. And then A, T, and B are all different factors that affect the magnitude. So A is called your amplitude of the vertical ground motion measured in micrometers. T is the period of the earthquake wave in seconds. And B is a factor that accounts for the weakening of the wave as it moves out from the epicenter. And the weakening of the wave could have to do with the kind of soil it's passing through. Okay, really hard ground, the wave is probably going to propagate through it more so than if it was really soft ground. That soft ground might absorb the wave a little bit. And a problem you might see, let's see, like number 52 in the homework. Okay, I'm just going to put it up and show you how you'd have to do it. They say, what is the magnitude on the Richter scale if A is 250, T is 2, and B is 4,250? Calculate R. All you have to do is just plug in 250 for A, plug in 2 for T, and plug 4,250 in for B. Use your calculator, and it'll tell you the magnitude. Okay? That's the last problem in the homework. Okay. Does everybody have that formula? Okay. All right, so that's the homework for tonight. Okay, on 293, that's 5.4 part 1. And page 301, that's 5.5. Okay, remember that's not due until Wednesday. Okay, so I'll see you guys on Wednesday. Okay, we'll go over that. And that's pretty much all we'll do Wednesday because of the short week. Okay, if you have any questions or you get stuck on it, feel free to stop by tomorrow. Remember, I will be here from 11 to 12 for extra help before parent-teacher conferences, but I will not be after school.